It's a pleasure to be here both to help celebrate this exciting center and the extraordinary accomplishments of John Clark, as well as the many students that he has generated in this field that are driving it in such exciting directions. I was going to say more about you, John, but enough about you for now. Let me talk a little bit about something different, which is about the solid state, and some recent developments in this field based on the fact that it's surprisingly straightforward now to both create, manipulate, and read out single spins in a wide variety of semiconductor systems. Talk about how they might be useful for an interesting new class of devices. How our better understanding of materials is leading us to some industrial type materials to think about quantum information, and it's still in its nascent stage, but it's a pretty exciting development. And then, as Irfan gently requested in his strong email, to focus a little bit on challenges and opportunities in this field and where it might go. Is that okay? All right. But to leave you with the one theme for what I want to talk about is that in contrast to today's semiconductor technology, which is based on making very clean materials, we want to put the dirt back in the sense of controlled defects, and talk about how some of these defects are very interesting and the challenges that they're bringing to this field of quantum state control. So just to be sure we're all on the same page, it's actually a very old field where color centers have been used for decades and decades and decades for lasers, interesting optical sensing techniques, where based on the defect that's put in the semiconductor, one can change the electronic structure around that site with transitions that can lead from the UV to the infrared based on the choice of ion that's put in the lattice, either interstitially or through the creation of a vacancy. And these defects have actually a very nice spin structure that makes them look very much like a trapped atom. And in fact, one of the nice things about looking at defects in this field, it enables us to borrow a lot of the very clever techniques developed by the atomic physics community and apply them in the solid state. So these defects have a lot of surprises, which I hope in the next 20 minutes or so will become clear. They have surprisingly long coherence times, many of them persisting to room temperature. You can optically control them very quickly or electrically and read them out optically. And while there are a number of defects in materials such as diamond and silicon carbide, both carbon and silicon-based materials, many more semiconductors are appearing that host these defects to allow us to build unusual types of hybrid solid-state quantum systems. Now, just to give a sense of what's been happening with these defects in the last few years, the literature is very large and the time is very short. So I asked my students what their favorites were. So don't shoot me if your favorite isn't here, but I'll give you their email addresses at the end. So one nice thing is the beautiful work at Delft, where defects in diamond, the nitrogen vacancy center, was used to both entangle electrons over kilometer scale distances and do some beautiful Bell's inequality tests using these solid state materials. And it's led us to some better understanding of some of the foundations of quantum mechanics. In the more applied directions, there's been some recent work, as you heard about from Jeff's talk, with beautiful techniques that, say, Oscar Painter and others have developed to make very nice one-dimensional photonic cavities. And in some recent work at Harvard, by integrating silicon-based vacancies in diamond into one-dimensional cavities, one can have single photon optical switches to control the interference between these states and entanglement in very small systems. So I thought these were nice examples spanning the fundamental physics to some interesting network developments just in the last year or so to show the power of putting defects back into semiconductors. Seems like an odd thing to do. But there are challenges, and I was going to talk a bit more at the end about that, but one is how can you really take these types of defects and controllably build networks and quantum systems? It's a very big challenge. And there's been progress using industrial scale implantation techniques to make arrays of defects in materials such as silicon carbide, using reactive ion etching techniques to make arrays of systems in doped CVD-grown layers of diamond to make controllable systems. And I say these are generating beautiful proof of concept measurements, but still not at the level one would really need to build robust quantum networks. What I do like in this field that's happening is people are becoming much more precise in their characterization of quantum states in semiconductors. And these two recent examples I think are quite brilliant. One, Michelle Simmons' group in New South Wales, using STM techniques to place individual dopants in silicon with atomic scale precision. And Steve mentioned in his talk about the ability to make gates and spin to charge conversion in phosphor-doped silicon. And these types of techniques have led to those developments. And more recently, some works at national laboratories, such here at LBL and at Argonne, using Bragg scattering techniques to measure the strain at the picometer scale of defects to understand how can you really turn these defect states into atoms and really make them identical, a challenge that's yet to be met right now in this field. But they do produce really beautiful pictures. And what about applications? So while the community obviously is thinking about building qubits for quantum computation, in the solid state there's some other interesting avenues, both communication, imaging, and sensing technologies, and work done by John Mayman and Dan Rugar and colleagues at IBM have made some significant developments in taking these quantum states, scanning them over individual molecules, and approaching, not quite there yet, but approaching molecular scale MRI, which I think as many people here know would be an extraordinary development in science. The other is to think about sensors using these quantum states and variations to magnetic, electric, and thermal fields. Oddly enough, looking at the breathing as crystals expand and contract, looking at the change in the eigenfrequencies of the states due to the change in the lattice, turned out to be a remarkably sensitive thermometer on the scales of fraction of millikelvin per root hertz at room temperature and below, allowing people to do intracellular measurements and also other types of in vivo techniques for monitoring. And finally, just touching on what Jeff mentioned earlier, there's been extraordinary developments on trying to craft quantum materials to embed these types of qubit states into larger systems such as cavities, photonic bandgap systems, microdisks, pillar resonators, exploring a lot of the developments in solid state technology to be able to capture the light and try and approach the strong coupling regime where light and matter can be indistinguishable as a basis to generate secure quantum communication. So there's a lot happening right now in this field with defects, and this is just touching on some of the developments to give you a sense, I think, of how quickly this field has moved from the discovery by others, say at the Naval Research Lab and other places years ago, that these defect states produce beautiful spin resonance signals, to a birth of applications that are now appearing. So, in the spirit of AMO, let me just quickly point out why these defects are so attractive to physicists as a way to build qubits. Simply, a missing atom in a lattice with a nearby dopant creates a triplet state, a type of molecular state with a bound electron. And there are a couple of interesting things about this very simple lattice change. One is, because materials like this have an actual strain, the strain tends to lift the degeneracy of the spin states. So one can optically address spin up and spin down states in the absence of any magnetic fields, simply using the strain to lift that degeneracy. So for a technology perspective, this is great. You can do magnetoelectronics with quantum states without a magnet. And the splittings are about 2.8 gigahertz, so they're right in the microwave region, very convenient to address and manipulate. Now you can tune those frequencies with very small magnetic fields, refrigerator scale magnets, that tune the G factor at a few megahertz per Gauss. But because many of these dopants, say the nitrogen atom, they also have a nuclear spin, there's a hyperfine interaction between that bound electron and the nuclear spin, which can be controlled through pulse resonance techniques, allowing you to transfer the wave function from the one electron to the one nuclear spin. And because the nuclear spins have much longer lifetimes, every place you have an electronic spin bit, you have a nuclear memory. And the community is working very hard to try and capture that capability, to think about using local memories in larger scale networks. And finally, just to hammer down the fact that these trapped electrons really are like atoms, this very simple energy diagrams gives you a sense of the cycling transitions you can do in the solid state that again mimic much of the work that's going on in AMO. A pulse of unpolarized light can excite these electrons from the ground to the triplet excited state. The spin then relaxes through a series of intersystem crossings back into an m sub s equals 0 ground state. So at the end of the day, what that means is you excite these systems with a pulse of unpolarized light with very low powers, and you end up with a polarized electron. And because these energy levels are split because of the strain at 2.8 gigahertz, you can modulate that spin and drive this Rabi frequency very nicely with microwaves on chip, and then read out the spin through the optical emission process. So you optically prepare, microwave control, and optically read out. And this protocol is common for a plethora of defects in solid state systems, where one difference is the wavelength and the nuclear species. So the neat thing is it's actually a pretty simple system. And all of this happens in a large band gap. So in many of these materials, such as diamond, doing this in a 5 eV band gap means that many of these processes are robust not just at room temperature, but well above room temperature, up to 600-700 Kelvin. And for sensing applications, that's actually very interesting. And for real applications where materials will be relatively warm, like your laptop, it's nice to know that you can maintain the coherence at higher temperatures. So a few years ago, people just took naturally occurring diamond, looked at defects that you can see here in this luminescence image, take a short-terminated coplanar waveguide, drive this spin state at 2.8 gigahertz, and you can see the Rabi oscillation on the right, 1 electron spin at room temperature, pretty good signal to noise. And it was this type of data that made people realize there's a lot you could do with these quantum states on the desktop in solid state materials. And this particular sample was just a piece of diamond bought online. And if you look at the time scales, what was intriguing at the time is when you think about SD-RAM operation times, I was told to relate this to technology, right? Okay? Okay. Otherwise, I might not say this. All right. And you look at the pi rotation times from this data, you see that they're at least comparable. So when you think about how hard it's been to develop a classical technology with single charges, and now you look at a single spin whose quantum state can be controlled on the same time scale, also under ambient conditions, it makes you think that maybe there's an interesting direction for this field. And I have to agree with Steve, it's not quite a superconducting qubit, but we have a dream. You might not share that dream. We'll talk later. So let me explain a couple of interesting things that have come out of this, which I think demonstrate an interesting contrast to conventional electronics. And one is to explore Berry phase using these spins. Berry phase has obviously been around in physics for a long time, from the 1980s, beautiful work by Michael Berry. And a lot of us have been familiar with this, how it appears in the quantum Hall effect as you go through these circular orbits, right, and how you pick up a phase in the electronic band structure of the material, which explains the precise positions of the quantized conductance. And the interesting thing about Berry's phase is that you can think about it as a means of processing information, because unlike today's technology where we build gates based on interaction times, which are susceptible to noise, and energy levels that can be tuned, Berry's phase suggests that you could build a type of information circuit where the path is the information quantity. The velocity along the path doesn't matter, energy fluctuations don't matter, and temporal interactions don't matter. So it's an interesting idea mathematically, and now we have a single spin system where we can try this. We can use the tip of the spin vector in the Bloch sphere, trace out a path, and measure that, and see if we can use that as a basis to build a type of holonomic gate. And the interesting thing about this is if you add noise to a system along the path, it shouldn't make much of a difference, because it's the integral along the path. Adding noise along the path shouldn't matter. So it's an interesting example of how a quantum state might have an interesting advantage compared to a classical technology. So the idea here is to take the Bloch tip of the vector, move from the north to the south pole, add a phase, bring it back, and that's our bit of information. And we can measure that by doing quantum state tomography at every place along this path, project the information on the XY plane, and just measure Berry's phase. So time is short here, so let me just show you the data. And on the left is one particular spin in a sample of diamond at 20 Kelvin, to keep the lines a bit narrower, going from the south to the north pole, adding phase and bring it back to the south pole, adding different wedge angles, like slices of a tangerine, right? And using that to capture phase. So in fact, it works. You can actually manipulate this quantum state around the Bloch sphere, do your quantum state tomography, and what you see in the blue and the red curves are the projections on the XY plane of the phase contained in that particle as you move it around the Bloch sphere. Moving it through one loop, multiple loops. In the middle curve is an example of moving it clockwise and then counterclockwise, canceling the phase, just to be sure you're really measuring a phase. And on the right, just doing it many, many times as a fan plot. So these types of quantum states can be controlled in this manner, in this case all optically, and in this manner, again, barring an AMO technique. There wasn't time to go over the technique, but it's essentially coherent population trapping. By taking two different wavelength lasers, simultaneously exciting the state, but adjusting the relative energies and phases, you can position this particle at a particular point on the Bloch sphere and then measure it with the states I've described before. The real test about this for technology is to think about what happens when you add noise, something that experimentalists typically don't like to do, but we do in this gate. And just a synopsis is here on the left, where we can add noise. In this case, it's Ornstein-Ulbeck noise. It's a mean reverting type of noise that's often seen in experimental systems. to different wedge angles, which are the different color plots in the middle that you see. The yellow circle, if you can see it in the back, is the shot noise limit of our experiment. And what's neat in this data, if you add 8 degrees of noise to this one particle, you can see it still fits the noises within the shot noise. So it's rather unusual for a device where you add noise and you're still shot noise limited. You can add a lot of noise, 20 degrees, 30 degrees of noise, and you still have a pretty quiet quantum system. If you add noise normal to the path, though, which you can see in the bottom section here, sure enough, your signal tends to get noisier. There you're changing the integration. So sure enough, the signal should get noisier. But it means that there's a pathway for designing quantum states in a solid-state system that, in particular directions, will be largely immune to noise. Now, these operation times are in the microsecond times. They're sort of slow, and if you think about how you can push it faster, recently work at McGill with Awschalom and others again have taken what people have done with superconducting systems and AMO systems and try and port these theoretical ideas to solid-state systems and see if you can use super adiabatic transitionless driving by changing the pulse sequence designs and the pulse shapes, push the limits of the speed, and you can get a significant speed improvement by doing this, down to the nanosecond scale. So I thought these were interesting examples just to get a sense of how this field is moving, new ways you can manipulate quantum states using phase, and maybe where quantum bits have an interesting advantage over solid-state systems. Now, in the last 10 minutes or so, I wanted to talk about new materials, and as a condensed matter physicist, I feel somebody here needs to talk about materials. Is that okay? All right. So when you ask, why does all of this work in diamond, why shouldn't it work in other places? Doing some theoretical density functional theory calculations for some time with Chris van der Waals' group at Santa Barbara and Julia Galli's group in Chicago, the theoretical predictions suggested many, many solid-state conventional materials should host qubits. It just people hadn't looked. And because of limited time today, I wanted to talk about the first on the list, silicon carbide, because it's a very powerful commercial material for high-power electronics. And for those of us who are experimentalists, another nice thing is the costs of these two samples are the same. So for those of us who actually have to buy materials, a 4-inch wafer is about the same cost as a 2-millimeter piece of diamond. So I'm guessing some of you aren't so familiar with silicon carbide, and just a one PowerPoint snapshot gives you a sense of how pervasive it is in technology. Everything from MEMS systems to JFETs to high power amplifiers. It's very powerful because of the way you can change the doping, you can change the lattice designs, it comes in different polytypes. How many people know what a polytype is? 3? Shameful. Shameful, your center has a big goal. Okay, I'm not even going to explain it. Please, thank you. We'll move on. So if you take a wafer of silicon carbide and look for individual spin states, sure enough, they're there. They're actually in the near infrared, right in the telecom region, which is pretty interesting, right where the theory predicted, which is quite striking to me. And because this particular polytype I'm showing you has a particular lattice design, there are 3 distinguishable spin states in different crystal locations, each with its own Rabi frequency, each with a spin pointing in a particular direction. So what's quite extraordinary in this data is by tuning your spectrometer to the right frequency, you can identify the single spin in the lattice, know where it's pointing, measure its frequency, and find that surprisingly in these systems, which are just, in often cases, commercial materials, the coherence times are surprisingly long. They're a few milliseconds. And the reason this is surprising is that there are lots of nuclear spins in these materials, roughly 5% isotopes spread throughout the material. Nothing has been purified here, just standard wafers. And it made us wonder why the times could be so long when the material is so crappy. And just to give you a sense of why this is so important to us, if I try and look at the coherence times measured in materials like diamond as a function of time, where a lot of groups, including ours, have put significant effort into purifying materials with CVD growth, and these triangles you see here are isotopic enriched CVD growth to really remove the nuclear spins from diamond, people have reached quite impressive coherence times, but this blob here is a silicon carbide time from a commercial wafer with a lot of nuclear spins. So it's made us realize there's something we're missing in this field regarding coherence in solid-state materials. And by, again, borrowing some of the physics of AMO and tuning our excitation detection right to resonance frequency in silicon carbide, this is an example of the single spin qubit data you can get in commercial wafers with beautiful contrast ratios for this one spin, which suggests it really is an interesting avenue to think about moving forward to larger network systems. So why does this work? Well, we're not really sure, but we do something that experimentalists do in times of desperation. We talk to theorists. And Julie Galli in particular took this problem on and came up with an extraordinary finding, which in hindsight is really quite elegant, which is that even in these heteronuclear systems, that the spin pairs can be decoupled, say silicon-carbon nuclear spins with relatively small magnetic fields applied, effectively having a type of spin impedance mismatch between the energy levels. And what's more is by using binary crystals, such as silicon carbide, the locations of these nuclear spins are such that their interactions are relatively weak, based on the local lattice sites in which they're allowed to exist. So at the end of the day, what this means is that there are probably many materials out there that many of us have ignored, thinking they weren't pure or clean or ideal systems, that may actually be wonderful materials to think about building solid-state systems. The nuclear density alone clearly does not determine the coherence time in these systems. And as Steve said, you always want longer and longer times, and maybe this is a pathway to find them. Okay, so just two things before I wrap up here, which were both surprises, at least for us in this field. And the one was that in the process of doing some of these measurements and polarizing electron spin states for qubits in silicon carbide, the students found, in fact, Abram Falk, who's now at IBM, found that these spins would relax through dynamic nuclear polarization and could very efficiently polarize the nuclei. And in fact, he found if you got to regions where the ground states of the spins, of electron and nuclear spins, and the excited states had an anti-level crossing, the efficiency would approach 99% at room temperature. A pretty amazing result, meaning applying a 30 millitesla field at 300 Kelvin to these materials and illuminating with them with light, you end up with a 99 polarized nuclear material. And just to put that in perspective, that's cooling the nuclear bath to a few microkelvin with densities of 10 to the 16th or so per cubic centimeter. So it's a very efficient way to create polarized nuclear states in semiconductors, which are interesting not just in perspective of memories, but also in perspective of having high contrast agents for magnetic resonance imaging. And because the T1 times on these are quite long, there's some interesting applications. Now, these are commercial wafers from Cree, and it's sort of fun to note these are the same wafers that are used to build LEDs that you pick up at Home Depot. That's why there's a Home Depot symbol. They're basically disordered materials. You grow nitrides on top of them with a small oxide layer for processing, and these same materials have quite high nuclear polarization. So the fact that you can prepare spin-polarized electrons and now polarize the nuclei very efficiently, both of which are somewhat unusual to be able to do in the same material, means that if you excite them simultaneously, you can entangle them. You have an electron spin, you have a nuclear spin, which is usually quite difficult to manipulate at the single spin level. And Paul Klimov showed relatively recently that if you do this properly, you excite the pair, you can create ensembles of entangled states at 300 Kelvin in these wafers. Now, these aren't individual states. There are 1,000 hybrid registers, each one an electron and nuclear spin pair, all of these with about a 40 micron cubic volume, but with no materials preparation and basically sheer luck at looking at these industrial materials, the fidelity is approaching 88% of these ensembles. So again, I would argue it's not at the level for going out and selling a machine, but it's amazing you can pick these wafers off online, create entangled states with high fidelity at room temperature with near-infrared optical technology that couples nicely into the telecom band. So I'm very hopeful about where this field is going, and I think a lot of it is that we're moving very fast on a highway on low beams. We're not really sure where we're going, but we're going there very quickly. It would be funnier if it actually wasn't true. So where do I want to stop here? I hope I've given you some interesting examples of both some exciting physics that happened in exploring the foundations of entanglement using solid-state materials, that one can begin to look at geometric phases in solid-state systems, in materials with very high nuclear polarization, generate ensemble entanglement. And where is this going? I think Jeff touched on some of this as well, but one very exciting direction in this solid-state field is quantum transduction, moving quantum states between spins, photons, and microwave photons that can couple to superconducting systems to build hybrid networks. And I personally think in this coming year we'll hit that. Not we, but someone in this field. I think we're at the point of having strong spin photon cavity coupling, which will enable some extraordinary pathways for quantum communication. And I'm very bullish in the fact that I think we will have wafer scale quantum technologies hitting us in the next few years. So thank you very much.
Do we have questions? One over there.
Yeah, Jeff. Oh, sorry. Oh.
So in terms of wafer scale quantum technologies, presumably you're not talking about single spins in most cases, because it would probably be hard to get each device to have a single spin across the wafer. Can you spell out your vision for what kinds of objects you might be doing?
Yeah, that's a great question, and obviously that's a big challenge for the field. So I think personally it will be possible to have a single spin technology at wafer scale, but not by placing single spins in specific locations. As you point out, will be really not impossible, but challenging. But I don't think it's difficult to think about building larger scale objects such as cavities that couple to single spins that are distributed across the wafer and be able to communicate between those structures optically. That I think is very possible.
Jeff?
So you mentioned that in one of your materials that homonuclear species are never near its neighbors.
In binary crystals.
Explain that. What about the crystal formation? Does it let these come together?
So you can have next nearest neighbors, and further neighbors than that, but in a, say, silicon carbide, where there's specific lattice sites for the silicon and carbon, yeah, right, it's based on the stoichiometry. Obviously you can have that, but not in these types of crystals.
I'm wondering if you could comment on whether there's any interplay between your very high nuclear polarization that you can get and the first statement you made, which is that this guy is very insensitive to nuclear spins in this very dirty material.
Now that's an excellent question, and I really wish I could answer it well. So if you'd asked me that question 6 months ago, I would have said, well, a very high nuclear polarization will tend to unify the field environment and allow for a higher coherence time. Now it's looking that maybe if you have a small degree of nuclear spins placed in the lattice, that you can anneal the local fields through fluctuations and actually maybe get to lower levels. So it may well be that both extremes are what you want. It could be that the decoupling of the nuclear spins leads to this longer coherence time, which is what you're suggesting. And I think that's something we need to look at further. It's a good question.